So we're going to go over the basic periodic trends that are based on the organization of the table, and there's three basic trends we're going to talk about. The first one is the atomic radius, in other words, what happens to the size of an atom as you go across and as you go down. Secondly, we're going to talk about ionization energy, what happens to the energy to pull an electron off as you go across and as you go down. And third, we're going to talk about electronegativity. And electronegativity is how much it wants to pull electrons towards it. And we're going to talk about how does that change as you go across and as you go down. Alright, so before we do that, let's talk really quick about the differences as in the electrons themselves as we go across the table. So if we go straight across, we're going to ignore these transition metals for now. They're still metals. They're always going to form, if they are going to form charges, they're always going to form positive charges, but we're not going to talk about what kind of charges right now. So everything here ends in S1. It has one valence electron. Everything in this column has two valence electrons. And as we go across, 3, 4, 5, 6, 7, and then everything with the exception of helium, they all have 8. And 8 represents having a full outer shell. So this is how the table is organized, and this is going to determine the behavior of the atoms as well. Not only that, but when atoms react, they're going to react in order to get what we would say is a full outer shell. Now they're either going to do one of three things. They're either going to gain electrons, they're going to lose electrons, or they're going to share electrons. Alright, and we're not going to really talk about sharing. We're going to talk about gaining or losing. Now if an atom wants to have 8, and right now it has 1, its choices would either be to gain 7, and then it would have 8, or if it loses that 1, then the shell beneath it is already filled. So by getting rid of that extra 1, it would now basically have a full shell beneath. So the easier thing on these are going to be to lose 1 plus 1. Second column, they have 2. Are we going to gain 6 or lose 2? They're going to lose 2. So everything in the second column tends to form a plus 2. Now we go over here to the third column. Again, we can either gain 5 to get to 8, or if we lose the 3, the shell beneath is already full, so these are going to form a plus 3. And just a reminder, this doesn't mean add 3. This means it has a plus 3 charge because it's missing 3 electrons. These we're going to say share because it's not very easy to gain 4 or lose 4. Technically, some of these way down here do actually lose 4, but for now, ignore these. Now, these have 5. You could either gain 3 to get 8 or lose 5 to get rid of that outer shell. It's going to be easier to get a negative 3 charge, gain 3, than to lose 5. The next one, 6, they're going to tend to gain 2 to get 8, and these have 7, they're going to tend to gain 1 to get 8. So, in essence, what am I saying here? So, here's what I'm basically saying to you. If we were to draw a really quick makeshift table here, 1, 2, 3, 4, 5, 6, here's what you're going to want to do anytime that you're given a table. You're going to go 1, 2, 3, 4, 5, 6, 7, 8. That's the number of electrons they have in their outer shell. And then you're going to go plus 1, plus 2, plus 3, x, minus 3, minus 2, minus 1, x. What does that mean? That means these have 1 in their outer shell and they tend to lose 1. These have 2 in their outer shell, they tend to lose 2 and form a plus 2. 3 in the outer shell, lose 3. 4 in the outer shell, tend to share. 5 in the outer shell, they tend to gain 3. 6, gain 2. 7, they gain 1. 8, they tend to be unreactive. And that sort of is an overview that will help you in understanding the trends in the periodic table. So the first trend we're going to talk about is the atomic radius, which is basically the radius of an atom, which is, just like in math, this would be your radius from the nucleus to the outermost electron. And the trend is that as you go down a group, remember the groups are vertical, then the atomic radius gets bigger. And as you go across the same row, the radius gets smaller. Now, why does that happen? Well, as you're going down, we're adding a whole nother energy level. For example, this is n equals 1. The next level we're at n equals 2. So if we look at them, this would be the atom. The one right below it would be bigger because it would have 2 energy levels. And the one below that would be even bigger because it would now have 3 energy levels, etc. As you go across, it's a little more difficult to picture, but you're basically adding electrons to the same energy level. So now there's 2, and then now there's 3. And what happens is, because the nucleus is getting more protons and you're adding more electrons, but you're adding them to the same level, the nucleus and the electrons basically get a tighter pull on each other. The nucleus basically hugs them even closer. So as we go across, the atomic radius gets smaller. So if you look at this, this really gives you a good idea. These are all in the same column, and we're talking about atomic size. So what happens is hydrogen ends with 1s1. Lithium ends with 2s1. Sodium ends with 3s1. It's pretty easy to see that as you go down, they all have 1 electron in their outer shell, but you've added an entire extra level, so they're going to get bigger. Very straightforward trend. Okay, so why does the size get smaller as we go across? Because we're adding another electron and another proton as we go across. Sodium has 11 protons and 11 electrons, 12, 13, 14, 15, 16, 17, 18. But as we're adding electrons, we're adding them all to the same level. In other words, sodium ends with 1s2, 2s2, 2p6, 3s1. So it has 1 electron out here far, far away from the nucleus, and so there's an attraction. Magnesium has 12, so it has 1 more proton, and it also has now 2 electrons in the outer shell. The protons and the electrons can pull even tighter. Now we have 13 protons, and we have now 3 electrons in the outer shell that can be pulled closer. And then number 14 has 14 protons and 4 electrons in the outermost shell, so it can pull them even tighter. So as we add more electrons to the same shell, the attraction between the protons and the electrons increases. So by the time you get over here to argon, there's a very, very tight attraction holding them very close to each other. Alright, so sample problem. Let's say, which one of these is larger, carbon or fluorine? We go to the table. Here's carbon. Fluorine, same row, but further to the right. Therefore, carbon is going to be the bigger one because they get smaller as you go to the right. In fact, I recommend when you get your periodic table, immediately right off to the side, smaller as you go to the right, bigger as you go down, and that's the trend for size. Now let's say that you had carbon again and lead. Which one of them is going to be bigger? Well, if we go over here and find lead, it's all the way down here. That means lead's going to be bigger because it's further down. Now these are easy ones because they're in the same row or they're in the same column. But this really wouldn't be a whole lot more difficult if I gave you, for example, aluminum, and then I also gave you lead. Okay, so lead, here's aluminum here. And lead is 1 over from aluminum, but it's much, much, much further down. So lead would definitely be the bigger one. So ionization energy is the amount of joules, which is a measure of energy, that it takes to pull an electron off. To pull 1 electron off, that's called the first ionization energy. To pull a second electron off would be called the second ionization energy. To pull a third electron off would be called the third ionization energy, etc. As you go across the period, the ionization energy goes up. It's harder to pull an electron off. And as you go down, the ionization energy goes down. It's easier to pull an electron off. This makes sense because remember, as you go down, the electrons are farther and farther away from the nucleus. What's going to be easier, to steal an electron when it's right here, very close, or to steal an electron that's way out here far away. It's going to be much easier to pull off an electron that's far away because the nucleus is not pulling as tightly. So this is why it decreases as you go down. As you go across, remember these are getting closer and closer to having 8 in their outer shell. So as you go across, they're going to be less likely to want to lose electrons, and as a matter of fact, as you get over close to 8, they want to gain electrons because it's much easier for them to get to 8 by gaining than it would be by losing. Alright, so nonmetals tend to form negative ions. They are all going to tend to gain electrons. So for example, nitrogen forms a -3, chlorine forms a -1, oxygen forms a -2. It's based on their location. I showed you this before. If we go over here to the right side of the table, they go -3, -2, -1. Nitrogen would be here, chlorine is here, oxygen is in this column, and by looking at these columns, the easiest way for this to get a full outer shell is to gain 3, and it'll look like this noble gas. If oxygen gains 2, then it will look like a noble gas. And if chlorine gains 1, it will look like a noble gas. So oxygen forms a -2 because by forming a -2, it now has 8 in its outer shell. When chlorine gains 1, it now has 8 in its outer shell. When nitrogen gains 3, it now has 8 in its outer shell. And the easiest way to get to 8 is to gain. Alright, so these are all in the same column. Lithium, sodium, potassium, rubidium, cesium. They're all in S1. So they all tend to lose 1 electron. Lithium, what its regular size would look like, would be more like this. When it loses an electron, it gets smaller. Sodium was also bigger. When it loses an electron, it gets smaller. Cesium was really big, and when it loses an electron, it gets smaller. They always get smaller when they lose an electron. Now notice, they still get bigger as you go down. Why? Because sodium was already bigger than lithium, and potassium was already bigger than sodium. So if they all have the exact same charge as each other, just ignore the charge and go by the original rule. Because lithium is the smallest and cesium is the biggest in the column, if they all form an ion with the same exact charge, they're still going to be the smallest to the biggest. Now, if you were asked, what about cesium plus 1 versus cesium, which one would be smaller? The +1, because they always get smaller when they lose. And this is actually an even better example of this. If we look at what happens as we go across. So these are all in the same row. When lithium loses an electron, it gets smaller. And beryllium, which ends with S2, it tends to lose 2 electrons, and it gets even smaller. And this one loses 3. And this one, typically it shares, but they're showing it as losing 4. Anytime you lose electrons, you get smaller. And the more electrons lost, the smaller it is. So if you were given any 3 things, aluminum +3, iron +2, and let's say sodium +1, and you were asked which one's the smallest, whichever one's the most positive is the smallest. The more electrons it loses, the smaller it's going to be. And notice the opposite is true also. These are actually, they go in this direction on the periodic table, but whichever one has gained the most electrons ends up being the biggest, because now it has more electrons than it can control, and the nucleus can't pull them as tightly. So gaining 3 electrons is going to make something much, much bigger than when it just gains 2 or when it just gains 1. Alright, so sample problems. Remember ionization energy. The rule was it goes up as you go across, it gets lower as you go down. So let's say I give you sodium or barium, and I would ask you which one has a higher ionization energy. Well, sodium is here. Barium, it is 1 over, but it's way down here. So what's our rule as we go down? The ionization energy is lower. So barium would have a lower ionization energy, and sodium would have a higher ionization energy, meaning it would be easier for barium to lose an electron than it would be for sodium to lose an electron. And we saw this in the lab. If you recall, in the lab, we had magnesium and we had calcium, and we put them in water. Magnesium didn't react in water, but calcium did. In acid, they both reacted, but calcium reacted more. Why? Because it's easier for calcium to react. It's further down, and it takes less energy for it to lose its electron, which is what's happening when it goes through the chemical reaction. And the same thing is true in the little video we saw, where we looked at sodium versus potassium versus rubidium versus cesium. As you go down, this one makes a bunch of hydrogen and then catches fire. This one catches fire right away. This one catches fire and has a massive explosion. And this one had the most massive explosion of all. Because as we went down, it took less energy for it to react. So it became much, much more reactive, less stable. On the other hand, let's say you were given boron and fluorine, and you were asked which of those two has higher ionization energy. So in this case, we're going across. Remember, the closer we get to 8, they want to hold on to their electrons. It's going to take a lot of energy to steal one from fluorine than it would from boron. So the higher ionization energy would be for fluorine to lose an electron than for boron. All right, and we can actually call these, if we have ions with the same exact number of electrons, we call them isoelectric or isoelectronic. So for example, aluminum has 10 electrons. Magnesium also has 10, sodium has 10, neon has 10, etc. Neon has 10 protons. Sodium has 11 protons. Magnesium has 12, and aluminum has 13. This is protons. Fluorine has 9 protons, and oxygen has 8 protons, and nitrogen has 7 protons. And I'm just getting this off their number on the periodic table. Here's my point. So what's important here is the ratio. And notice, for example, for neon, it actually has the exact same number of protons versus electrons, 10 and 10. So if you imagine that one as being, let's just say, this size. Sodium has more protons than electrons. It is going to actually be smaller because it can control its electrons better. And then magnesium is going to control its electrons even better because it has even less electrons to control. Aluminum has even less electrons to control. So the +3 would always be the smallest. As we go the other direction, now fluorine only has 9 protons. It's not going to be able to control all 10 of those electrons as well, so it's going to be bigger. Oxygen has 2 extra electrons, and nitrogen has 3 extra electrons. So as we go across, the -3 one is always going to end up being the largest because it's got 3 extra electrons it's trying to control. And this diagram just shows you the same thing. Notice size-wise, the more negative it is, the larger it's going to be. The more positive it is, the smaller it's going to be, with the neutral one being right in the middle. And these happen to be isoelectronic. They all have the exact same number of electrons. The truth of the matter is, though, if you go to the periodic table and you have, let's say, a neutral atom up here, and then something with a -3 charge that's way down here, the negative one's going to always be bigger. Or let's say it's way down here and it has a +3 charge. Even though it's way further down, it's going to end up being smaller because losing electrons makes such a huge difference in size. The final trend is electronegativity. This is how much an atom pulls electrons towards it. It has the same trend as ionization energy. Lower as you go down, bigger as you go across. For this one, the noble gases don't count because they're not pulling electrons towards them at all. They're very happy with how many they have. The highest on the entire table is going to be fluorine, this one right here in the upper corner. And so it gets bigger as you go across. Fluorine pulls the hardest. It's got 7. It really just wants one more. It's going to tend to pull one towards it. As you go to way down here, these didn't have much of an attraction for electrons at all. they actually were much more active and ready to give them away. So these down here, like cesium and francium, are going to have the lowest electronegativity. So if you were doing practice problems with this, you would look at the periodic table. The closer it is to this bottom corner, those are going to be the lowest electronegativity. And the closer it is to this top corner, those are going to tend to be the highest electronegativity. And remember, the noble gases won't count.